In this video, I want to take a look at the first law of thermodynamics for open systems. This is a topic that you will run into, I'd say halfway through an undergraduate course in thermodynamics, and you also need to know about it for the FE exam. So let's look at the most general form of the equation, and then I'll try to get in some practical examples of when you can use the first law for open systems and how to quickly recognize the form that you need. So we're talking about first law for open systems, and you can write it this way. Q dot minus W dot, and I'll write it and then we'll talk about each of the terms, plus the summation of the mass streams going in times the enthalpy in plus velocity in squared over 2 plus g z in minus summation of the mass flows exiting. Then you have exit enthalpy for that mass stream plus the exit velocity squared over 2 plus g times the exit elevation. And all that is equal to 0. Now I just realized that's going to make no sense to you unless I show you an example. Right? This is a bunch of math. It's confusing. There's going to be no intuitive understanding for you. So let me take a few steps back and talk about where you would use this equation to begin with. What kind of system? I talked about an open system. An open system in thermodynamics is simply one where mass can cross a boundary. So maybe I've just got a box. Okay. And I've got an exit, and I've got an inlet. And let's say I just stick a hose here. So I'm pumping water, it's going through, it's filling the box, and it exits. And let's say this dashed portion, I'll say that is my system boundary. When you are dealing with open systems, you need to define a system boundary. So I have water entering the system and exiting the system. Just flowing water through. So that's an open system. Mass is crossing the boundary, coming in, and mass is also crossing the boundary going out. That's a very simple open system. So this right here, this would correspond to a mass going in, which corresponds to this term in the equation. And here you have a mass sub E for exit, a mass exiting that control volume. And we just drew as this box right here. I could also have a heat transfer going on. So maybe I have an electrical wire sticking in here, and got a voltage across that, and I've got current going through it, and this coil is getting hot, an electrical resistance heater. That That's what this Q term accounts for. So maybe this is a 10-watt resistance heater. And it's adding heat energy to my system of water. So that's where the Q term would come in. What about this work term? Well, maybe I've got this hose. I'm just putting water in and it's coming out. Maybe in here I've also have, see if I can draw this. See, I've got a turbine blade or a fan in here. Maybe I've got that fan connected to a drive shaft. Okay, so I've got these blades on a shaft. And maybe that water coming in is spinning those blades. That would be a work output. So hopefully this is making sense of some of these terms for you. Now what about this term? Well, this is lowercase h. That's an enthalpy term. The water is going to have a certain enthalpy coming in and a certain enthalpy going out. So it's going to have an enthalpy in at this point, right where it crosses the boundary here. And it's going to have an exit enthalpy right as it exits the boundary over here. It's also going to have an inlet velocity and an outlet velocity. It's going to have an inlet elevation and an outlet elevation. And in this case, the water going through isn't changing an elevation. Maybe if I had a control volume like this. So if I had a fluid entering here and exiting here, and let's say this was the ground, got a big tank sitting on the ground, well then obviously I'm going to have an elevation change. Some on elevation change x, that's 10 feet. And that is a potential energy change, which these terms, this GZ term here and this GZ term there, take account of. So that's what those are for. And this whole equation is just an energy balance. The first law of thermodynamics says that energy cannot be created or destroyed. The energy can only change form. And one of the ways it changes form is from potential energy to kinetic energy, or potential energy to velocity. So we looked at the Q term, the heat transfer term, the work term. We had an example of a mass going in. I could have, maybe I've got water entering here. Maybe I'll also have, maybe have an inlet here where I have, I don't know, oil going in. And that summation sign just says, hey, you can have more than one mass flow crossing into the boundary. Or I could have more than one thing coming out. Right now, just have water coming out. Well, maybe I have some oil coming out over here at this exit. Maybe that's a exit 2, and that's exit 1. That's an inlet 1, and that's maybe this is an inlet, a second inlet. That's what that summation sign is for. Velocity can change. If I had a nozzle, maybe I've got a nozzle that looks like this, and my boundary is this. My boundary is basically the nozzle, and let's say, I don't know, maybe I'm passing air through that nozzle. So I've got air in and air coming out. And if I'm using a nozzle, I'm going to have some inlet velocity, V sub I, and I'm going to have some outlet velocity, V sub E. And just looking at the nozzle, you can tell the exit velocity is going to be greater than the inlet velocity. So that's what this term here and this term here takes account of. It's balancing energy due to a velocity increasing or decreasing. And then you have your enthalpy terms. Enthalpy can change for a number of reasons. If you have a fluid and it's doing work, then it's losing specific enthalpy. Or if you have a fluid and you're adding heat to it, then the exit enthalpy might be greater than the inlet enthalpy. So those terms take account of that. And unlike the first law, there's no internal energy because that's contained inside the enthalpy term. Enthalpy equal to U, internal energy, plus pressure times volume. So there's a U term actually hidden inside the H term. That is an introduction to the first law of thermodynamics for open systems. I hope that gives you a good idea for what each of the terms in the equation mean. I'll try to do another video where I get into more specific examples and see when is Q positive or negative, when is W positive or negative, and how this equation can be greatly simplified for certain scenarios. If you have any questions, please post a comment below. Thanks.